In this video, we're going to talk about nuclear stability. Um, so not all nuclei are stable, and that's where we get radioactive nuclei from. Is they're unstable and they're trying to become stable, and so we see that it's the ratio of the neutrons to the protons that's important in measuring and predicting the stability of a nucleus. So I'm going to give you a couple terms real quick, and this might already be on your lecture notes. But N is going to be equal to the number of neutrons. And Z, remember, is our atomic number. And that atomic number is going to be equal to the number of our protons. And so we're really looking at a ratio between our neutrons and our protons when we're evaluating overall stability. So if our N to Z ratio is too high, so I have more neutrons than protons uh, for what's ideal, then we're going to see our unstable nucleus decay to something more stable by converting our neutrons into protons. And this will happen by beta decay, which we'll talk about some more in a bit, but we're essentially taking a neutron, which has no charge and a mass of 1, and converting it into a proton with a charge of 1 and a mass of 1. And we can do that by emitting an electron, essentially. So if I add to that a -1 charge with very negligible mass, they would sum up to a neutron. The charges would cancel. And so a neutron can be converted into a proton by also creating an electron and then having that leave the nucleus. If our N to Z ratio is too low, I mean, we don't have enough neutrons for the number of protons to reach a stable arrangement, then we're going to see the opposite happen. We're going to see a proton converted into a neutron. And it can do this in a number of ways. It can either do this by electron capture, where it grabs an electron and combines it with a proton, and that converts into a neutron. Or our proton can be converted into a neutron by separating its charge from its mass and emitting what we call a positron particle, which is just a positive electron, essentially. And so either of those would work. We could also do it through alpha decay, which takes a lot longer, but that's another option as well. And these types of decay we're going to talk about here in another lecture or two. So here's actually an interesting, I like this chart. Here's an interesting chart showing all of our different like common isotopes for different elements. And what it's plotting is the number of neutrons here on the y-axis and the number of protons on the z-axis. And so this black line right here is a 1-to-1 ratio of protons to neutrons. And our blue dots here are stable nuclei, and the green ones are radioactive, so they're unstable. So you can see immediately, first impression is that there are more unstable nuclei than stable nuclei on our periodic table, like in the universe or our planet. And some other trends you'll notice here is that our nuclei that are in a 1-to-1 ratio of our protons to neutrons that are small in mass tend to be stable, but that as the mass increases, that behavior changes. A 1-to-1 ratio isn't stable for something with a large mass at all. And so that linear 1-to-1 relationship isn't something that holds for stability in nuclei, which means that to kind of see these general trends, we have a few different kind of rules. It's like, well, is it a small or large atom? And that will help me kind of navigate whether or not I think something will be stable or unstable. So for those first 20 elements right here that I circled in blue, there, it's a nucleus will be stable if you get the ratio close to 1 nuclei to protons. Then for our kind of next region from 20 to 40, so in this region right here, if that ratio approaches 1.25, we'll have a stable nucleus. And then looking at 40 through 80, so that's these ones right here, we'll find that a ratio of about 1.5 neutrons for every proton gives us our most stable arrangement within a nucleus. And anything above 83, it's just there's nothing that's actually stable. It's too heavy to be stable. And so these all here are all unstable. Let's look at an example of one of these. Let's look at krypton 85. So if I was just pulled krypton 85 off the periodic table, it's like, is that one going to be stable or not? And I wanted to predict it, I could. Um, so looking at krypton 85, that's the mass number, and its atomic number is 36. So I need to know the number of neutrons to actually decide if this is going to be stable or not. I know I have 36 protons. So to get my neutrons, it's 85 minus that 36, which is going to give me 49. So I'll have 49 neutrons in this nucleus. So I'll calculate the N to Z ratio, which will be 49 neutrons for every 36 protons. And when I calculate that value, I get 1.36. Now, if this was a very heavy atom, then that would be fine. And if it was a really small atom, it wouldn't be fine. So we have to then kind of place krypton in these four ranges of nuclei. And since it has a atomic number of 36, it falls into the second category where atomic number is within the range of 20 to 40. And so a ratio of 1.25 would be stable. And since this is actually larger than 1.25, we have an unstable nucleus. And knowing that it's got a higher N to Z ratio, that actually tells us that we expect some of those neutrons to decay into protons. Sorry, 0. So we expect more protons to form to become stable. And now we're going to start looking at what does this decay mean, and how do unstable nuclei become stable through a nuclear reaction. First, I want to tie this to binding energy. So we've looked at the N to Z ratio that tells us what's the most stable nuclei. But there's also this kind of idea with the ratio of a magic number, which I realize is kind of a silly thing or a silly name for something in chemistry. But there's a few magic numbers of stable nuclei that are just really stable. And so it's kind of similar to a noble gas electron configuration. It's like this principle that it's nuclei are going to try to get to the most stable possible nuclear arrangement, similar to something that's already there that's very stable. And so we'll see that our nuclei are most stable when either the number of protons or neutrons equals 2, 8, 20, 28, 50, or 82. Another one is just neutrons are hitting that 126. And just comparing these across like the number of stable isotopes on a periodic table, we see that in general that our even numbered proton, even numbered neutron nuclei tend to be more stable. We've got 157 stable ones with that even number of protons and neutron arrangement. Once our neutrons have an odd, or our protons have an odd number, we see that number of stable isotopes dramatically decrease. And if they're both an odd number, there's only 5. There's only 5 isotopes out there that have odd numbers of protons and neutrons that's actually stable. And so these are kind of some guiding ways to kind of also think about this. And the other way we can think about stability is, as we alluded to earlier, looking at the binding energy per nucleon for the nucleus. And so that's going to be, again, a measure of that total binding energy for the nucleus divided by the number of nucleons. And it's really measuring how much of the mass of our subatomic particles are converted into energy as that nucleus forms, which is a measure of the stability that's coming from the attraction through the strong force in the nucleus. And so we see that the relative stability of the nucleus can be predicted by its binding energy. So as binding energy increases, we see stability of the nucleus increase as well. And so this plots the mass number right here versus the binding energy per nucleon. And we see it kind of rises sharply, right? So as we increase in size, the binding energy of our nuclei increase rapidly. But then they start leveling off, which is interesting. And when we're at our peak here, it's going to be iron 56 that has the highest binding energy. And after that, it decreases. And so we'll see that particles in general are with really large mass numbers are going to be less stable, and they're going to try to change their nuclear structure to have a higher binding energy, to be more like that iron 56. And similarly for small ones, they're going to try to get to a larger binding energy, more similar to iron 56 when they're really small.